In this video, we're going to continue analyzing valence bond theory. We're going to look at some different types of hybridization for polyatomic molecules as predicted by valence bond theory. We've already looked at sp3 hybridization. We're going to continue to analyze that type of hybridization, but we're also going to look at sp2 hybridization and sp hybridization. So for polyatomic molecules where our central atom has two or more covalent bonds, valence bond theory, of course, predicts that the central atom, its atomic orbitals will undergo hybridization. The s and p valence atomic orbitals can combine to form hybrid orbitals. And also, the terminal atom can undergo hybridization if it forms a double or triple bond with the central atom. So there are instances where not only the central atom can undergo hybridization, but also a terminal atom can undergo hybridization if it forms a double or triple bond with our central atom. The number of electron domains for the atom, for our central atom, determines the type of hybridization that it will undergo. Now this is very critical. The number of electron domains around an atom undergoing hybridization determines its hybridization. So if you have 4 electron domains around your atom, it's going to undergo sp3 hybridization, and the hybridized orbitals will be tetrahedral in their geometry. If you have 3 electron domains, you will undergo sp2 hybridization, and the hybridized orbitals will be trigonal planar. If you have only 2 electron domains, that atom will undergo sp hybridization, and the hybrid orbitals will be linear. So this is very, very important to appreciate in order to determine the type of hybridization. So be sure you write all this, this table down. When you're analyzing hybridization for a molecule, there's certain steps that I like to follow. So write these down and then follow along when we practice some examples. The first thing you want to do always is draw the electron dot structure for the molecule that you're analyzing. Second, determine the steric number for your central atom, or the number of electron domains. Determine the number of hybrid orbitals needed for your central atom. And the number of hybrid orbitals is always equal to the steric number. So if you have a steric number of 4, you'll need 4 hybrid orbitals. If you have a steric number of 3, you'll require 3 hybrid orbitals for that atom. Next, determine the hybridization and the hybrid electron configuration. Remember, the table we just looked at allowed us to figure out what type of hybridization we have by looking at the number of electron domains, or the steric number. Finally, once you've determined the hybridization and where the electrons are in the hybrid orbitals, you want to be able to accurately draw the molecule by indicating all of the hybrid orbitals and how they overlap in order to form the bonds. So write these steps down, and then let's take a look at 3 examples to help illustrate how we might do this. The first molecule we're going to look at is ethane, C2H6. So pause the video, follow those steps, and see if you can determine the hybridization and draw ethane accurately. Okay. So the first thing we have to do is draw our electron dot structure for ethane. So you can see that drawn here, pretty simple. Next, determine the number of electron domains around our central atom. Now here, please note that we have 2 central atoms, 2 carbons, so we're going to determine the hybridization for each carbon. We don't combine them, we're looking at each one. So each carbon has 4 electron domains. You can see 1, 2, 3, 4 bonds for each carbon, so we have a steric number 4. Well, if we have a steric number 4, that means that we're going to require 4 hybrid orbitals. Also from our table, you could see that we're going to have sp3 hybridization. So we'll look at that in just a second. So the next thing, let's look at the valence electron configurations for our central atom. Now I'm showing you here 1 carbon, but again, we have 2 carbons which are identical in their bonding, so multiply this times 2 essentially. So each of our carbon central atoms has an electron configuration of 2s2 and 2p2. Now let's look at the hybridization for our central atom. Well, we said that we had 4 electron domains. We had a steric number of 4, so we required 4 hybrid orbitals. What that means is that we're going to require 4 atomic orbitals to make those 4 hybrid orbitals. So we're going to take the 2s, and all 3 of our 2p orbitals and combine those to form 4 what we call sp3 hybrid orbitals. So those 4 atomic orbitals now combine to form our hybrid orbitals. Now let's write the electron configuration for the hybridized orbitals. For carbon, for each of our carbons, we have 1, 2, 3, 4 valence electrons. So we're going to follow the Aufbau principle and Hund's rule. We're going to put 1 electron, one of our 4, into each of our hybrid orbitals. Each electron has the same spin. So now what this tells us is that each of our 2 carbons has 4 hybrid orbitals, sp3, and each of our hybrid orbitals has 1 electron in it. So we've taken our s and our 3p orbitals and we've combined them to form 4 sp3 hybrid orbitals. They're going to be tetrahedral in geometry, and each one will contain a single unpaired electron, all with the same spin. So if we draw that, here's what it would look like. So this is our C2H6 molecule drawn representing the, showing the hybrid orbitals. So pause the video and let's take a look at this. So what you see here, here's one of our carbons, and you see that we have our 4 hybrid orbitals, and we're trying to draw them here all in a tetrahedral geometry. Here's our second carbon, again with our 4 hybrid orbitals, all drawn with sp3 hybridized orbitals. 2 of those hybrid orbitals are going to combine here in a head-on fashion to form the carbon-carbon single bond. The other 3 hybrid orbitals are going to overlap with one from hydrogen, hydrogen's 1s orbital. Now remember, each of our hybrid orbitals has 1 electron, and hydrogen is donating 1 electron, so we're going to end up with a shared pair of electrons in the region where the orbitals overlap. So here you can see we've represented the electrons forming each bond. Now all of these bonds are what we would represent as a head-on bond, so we call those sigma bonds. So here, all of our covalent bonds that are formed are categorized as sigma bonds. So let's take a look at a different molecule. This is ethene, C2H4. Now that you've seen ethane done, pause the video and see if you can do the same thing for ethene. Determine the electron configuration for the hybridized orbitals, and then accurately draw the molecular shape for this molecule. Pause the video and give it a try. So for C2H4, we of course want to draw our dot structure first. And here you can see we have a carbon-carbon double bond. Next thing, let's determine the number of electron domains around our central atom. We have 2 central atoms, so each one is basically identical. The number of electron domains, we have 1, 2, and a double bond counts as 1 electron domain. So each carbon has 3 electron domains, so each one has a steric number of 3. Remember that we require 1 hybrid orbital for each electron domain. So for each of our carbons, we're going to need not 4, but 3 hybrid orbitals. So this one's going to be a little different. So let's look at the electron configuration for our carbons. The ground state electron configuration for an isolated carbon is 2s2, 2p2. And now let's look at the hybridization that these carbons will undergo when they form a bond. For this molecule, we said that we needed 3 hybrid orbitals. So for 3 hybrid orbitals, we only need 3 atomic orbitals. So we're going to take the 2s and only 2 of the 2p orbitals. So we need 3 hybrid orbitals, so we take 3 atomic orbitals to make those hybrid orbitals, the 2s and the 2p. Now note, this 2p orbital here does not disappear. It's still there. And so we call these sp2 hybridized orbitals because they're 1 part s and 2 part p. So here you can see we have our sp2 hybrid orbitals, all have the same energy, and here's that 2p orbital. It's still there. We can't destroy orbitals when we undergo hybridization. So next, let's add our electrons. We started with 4 electrons in each of our carbons, and so we have to place those one at a time. 1, 2, 3. Now here, our 4th electron will not go back into the sp2, it will go into the 2p. The energy difference between these orbitals is fairly small, and so we place 1 electron in each of the hybrid orbitals and then 1 into the 2p. So now we've placed all 4 of our electrons. So now, for this hybridization, we took 1s and 3 p orbitals, but we only used the s and 2 of those p orbitals, so we formed 3 sp2 hybrid orbitals, and then we still have 1 unhybridized or unchanged p orbital. Now here is how those orbitals are going to be arranged in the correct molecular geometry. The 3 hybrid orbitals, remember we had 3 electron domains, which tells us that they're going to be trigonal planar. So here in kind of green, you see the hybrid orbitals all trigonal planar. The unhybridized p orbital is going to be perpendicular to those. So take some time and analyze this. Be sure you convince yourself of how the orbitals are going to be arranged in 3-dimensional space. So now let's draw those. Here we have our 2 carbons. Each carbon has 1, 2, 3 sp2 hybridized orbitals. Here's the 1, 2, 3, and these are trigonal planar to each other. We have our 2p orbital. This is 1 2p orbital, and this is 1 2p orbital, and those are perpendicular to those trigonal planar orbitals. So each of our hybrid orbitals has 1 unpaired electron, even the 2p has 1, and then our hydrogens have 1 unpaired. So we have our electron pairs here, forming our covalent bonds between the carbons and the hydrogens and the 2 carbons. And here's something special we haven't talked about. Our unhybridized 2p orbitals, each of those has a single unpaired electron. You can see here and here, and these have opposite spins. So our 2p orbitals are going to be able to overlap to form that double bond. So here our single bonds are all sigma bonds. They're all head-on bonds. But these, as we mentioned before, our 2p orbitals, each with 1 electron, those guys are going to kind of overlap. And again, this is one, what we call a pi bond. So our 2p orbitals are parallel to each other. When they overlap in a parallel manner, they form a pi bond, unlike the sigma bonds, which are head-on. So these p orbitals kind of fuse together, and this is, I want to stress this again, this is one bond because it's formed, we have 1 shared pair of electrons, and this is the overlap of 2 atomic orbitals. So this is 1 pi bond. So our double bond is made up of 1 sigma bond and 1 pi bond. Here's a little more colorful, maybe a little better representation of that pi bond and the geometry of C2H4. Pause the video and take some time to analyze this, and be sure you convince yourself of how these are spatially arranged and how the p orbitals overlap. So pause the video and take a few minutes to look at this. So let's take a look at the hybridization and the molecular geometry for one more molecule, ethyne, C2H2. Pause the video and see if you can determine the hybridization and accurately draw this molecule. So the first thing we want to do is draw our electron dot structure. Here we have a triple bond between our 2 carbons. So we need to determine the number of electron domains next. Each of our carbon has 2 electron domains because, of course, a triple bond counts as 1 electron domain. So each carbon will have 2, and a steric number of 2. So therefore, we require one hybrid orbital for each of our electron domains. So each carbon requires only 2 hybrid orbitals, not 3 or 4 like in previous examples. Let's look at the electron configuration for a isolated carbon atom in its ground state. As always, we have 2s2, 2p2. And now let's look at the hybridization for our central atom. Now remember, each carbon requires only 2 hybrid orbitals. So we don't need to use but our 2s and only one of our 2p atomic orbitals. So we take the 2s and one of our 2p, and that's going to give us sp hybridization with 2 p orbitals left over. So our hybridization would look kind of like this. Here's our sp and our 2 unhybridized p orbitals. Now let's place our electrons. We have 4 electrons, and again, this is for each carbon. We put 1 electron into our hybrid orbitals, and then we put the remaining 2 in the unhybridized p orbitals. So now let's see if we can draw this. We have our s orbital and our 3p orbitals, but remember, for sp hybridization, we're only going to take the s and one of our p orbitals. So we form 2 sp orbitals, and we have 2 unchanged, unhybridized p orbitals. The 2 sp orbitals are linear. So here, kind of in green, is one, and here's the other. So those are our sp hybridized orbitals. And then we have our 2 p orbitals. One of them will be perpendicular along, let's say, the y-axis. The other will be perpendicular to the hybrid orbitals along the z-axis. So take some time, pause the video, be sure you understand how these orbitals are all arranged in in the correct geometry. So now let's put those together. Here we have our 2 carbons. Here's our sp hybrid orbital. Here's another. Here's sp for this carbon and sp for this one. We have our 2 p orbitals. One of them is perpendicular along the y-axis and one along the z-axis. Same thing here along the y-axis and z-axis. Let's put our electrons in there. We have a pair of electrons, one from the hybrid orbital, one from the hydrogen. That's going to form a sigma bond. And then each carbon will donate an electron, forming a sigma bond there. And then here's a second sigma bond. So we have 3 sigma bonds. And now let's look at our pi bonds. Our p orbitals are perpendicular here. So these 2 p orbitals, they're perpendicular, or excuse me, parallel to each other. Along the y-axis, those guys will be able to overlap and share that pair of electrons. That's going to form a pi bond along the y-axis, and we'll also be able to form a pi bond by these 2 p orbitals because they're parallel to each other, and so their electron clouds are going to be able to overlap and share these electrons, which again have opposite spin. So we'll be able to form a pi bond along the y-axis and a pi bond along the z-axis. So take a look at that and be sure you convince yourself that that's the case. Here's a little bit more of a colorful representation of it, where we have our hybrid orbitals, and then in red and blue we have our unhybridized p orbitals. Look at how the electron clouds kind of fuse together. So again, pause the video and convince yourself that these orbitals, of how they overlap and form these sigma and pi bonds. So be sure you understand valence bond theories applied to some of these larger molecules, be able to predict the hybridization, and more importantly, or just as important, accurately draw what these molecules look like in 3 dimensions with their orbitals.